Okay, so now let's take a look at this new method I've been alluding to for quite a while. So before I start, I want to make a couple of notes about vectors, because we're going to be using vectors to solve this problem. Specifically, we're going to be using the dot product. Now, hopefully by now you've all seen that we can use the dot product to find the angle between vectors, right? So that's going to be A, B, cos theta, where theta is actually the angle between them. Now, look, I want to represent that on a diagram. So let's say that that's vector A, and that's vector B, and this is the angle between. Alright, now what would happen if B was decided such that B had a magnitude of 1? Now, it doesn't mean that it's completely flat, it could be in any direction, but the key point is it's got a magnitude of 1. Well, that means that this here disappears. And I'm going to keep that on there. Okay, theta. So, looking at this here then, A cos theta. Well, that's in the form of a standard trig problem, right? Where A is the hypotenuse of the triangle. Okay, and B is the distance along the bottom, but the distance along the bottom is just 1, right? Okay, so what this is actually doing is it's showing that the dot product, if you were to make one of these two vectors have a magnitude of 1, then the dot product can be used to calculate the magnitude of A that is in the direction of B. So A dot B, if B is a unit vector, will calculate the magnitude of A in the direction of B. Okay. Now that's important because if B was a directional vector, like a unit vector, or like one of the axes, or like, well, anything else in these problems up here, then it means that if I could just get the direction in the form such that it's a unit vector, then I can just use the dot product to avoid all that nasty trig stuff that we were doing earlier. Right, that's the first thing I want to bring in about vectors. The second thing I'll get to in a moment. Alright, so now I'll show you what I mean, or how you can use that. We've got two directions that we care about. That's the first direction, and that's the second direction. Now, because we're talking about the line y equals x, I know that the direction along the line can be represented as the vector 1, 1, or 2, 2, or 3, 3. That's the direction of that line. Now, this isn't a unit vector though, because if I use Pythagoras' theorem, I get 2, not 1. So actually, I'm going to write that as 1 over root 2, 1 over root 2. Check it out. Use Pythagoras' theorem, it's now got a magnitude of 1. Right, so that's that direction. We've then got this direction as well. Alright, well, the thing is, when you're dealing with vectors, let's just do this in a general form, A, B. If I wanted to find a vector that is perpendicular to this vector, all I do is flip them round and make one of them negative, and it doesn't matter which one you make negative. Okay? So that means that this direction here will be minus 1 over root 2, 1 over root 2. Okay. So what I'm going to do now is I'm going to find the component of 8i minus j in both those directions. So we'll go for parallel first. Okay, well that would be 8 minus 1 with this vector here. So 1 over root 2, 1 over root 2. Well, we can actually calculate what that is, right? Because these things here are the same. It's 8 root 2's take away root 2. So that's going to be 7 over root 2. So, 7 divided by root 2 is 4.949. Okay, notice over here, that triangle that I drew down, pretty close, right? The reason why there's a discrepancy is because, remember, at the beginning of the first method I showed you, I had to round 7.125 degrees to 7 degrees. So that explains why there's a discrepancy here, right? And then all I do is perpendicular. Which will be 8 minus 1, dot product of minus 1 over root 2, taking this from here, right? And 1 over root 2. Well, altogether, that's going to be minus 9 over root 2. Which is 6.363. However, remember, the perpendicular part is the bit that's affected by this. So I now need to divide that by 4, which is 1.59. So divide all this by 4 is 1.59. 1.59. Now notice as well, if you're doing this calculation with me, I've ended up with a positive number here, whereas here I ended up with negatives. That's because the direction has changed. It was negative, now it's positive. Okay, so I've literally just decided to drop that sign because of the problem. Okay, all right. So that's 1.5909. Again, that is pretty close to this. Okay, it's actually a more accurate version of this. Okay, so now what I can do is say, well, look, there's my direction. That's the plane, y equals x, or the line, y equals x. I know that this direction away from the plane afterwards will be 1.59 that way, and it'll be 4.949 that way. So now all I'm going to have to do is apply Pythagoras' theorem. So squared plus 4.949 squared, square root the answer, which gives me 5.19. 5.198. So pretty close, but this is the better method. Okay.